Advanced Graph RAG 2, the next 5 families. Let's dig in. Quick orientation before the last leg. Across parts A through F, we built a memory that runs 2 clocks, tiles its facts into half-open intervals, closes contradictions instead of erasing them, and can answer what did we believe last April. Then we met 6 systems that each solve a slice of that. What is left is not another mechanism. It is the awkward part, deciding which of these things you should actually run. Every system so far argued from a score: higher accuracy, better recall, fewer tokens. The 2 we meet today argue from something else entirely. One asks whether a memory can improve itself without you writing a better prompt. The other asks whether you can prove, afterwards, exactly why the agent said what it said. Neither is trying to win a benchmark, and one of them, delightfully, does not report a single comparative number at all. SAGE stands for Self-Evolving Agentic Graph Memory Engine, out of Peking University and the Beijing Institute of Technology, posted to arXiv in May 2026. Its one idea is a feedback loop. A writer builds graph memory from interaction history. A reader retrieves from it. And crucially, how well the reader did becomes the writer's reward. The memory is not tuned by you. It is tuned by whether it turned out to be useful. Now, a footnote that matters more than footnotes usually do. Print the SAGE paper, and the bottom of page 1 reads 40th Conference on Neural Information Processing Systems, NeurIPS 2026. That is not an acceptance. It is what the NeurIPS style file prints on every paper typeset with it. The arXiv record carries no acceptance note and no journal reference, and the code link is still anonymized for review, so we cite it as a preprint. So how does the writer work? Not as an extraction pipeline. It is a policy making a sequence of decisions. It reads a document segment, and at each step it either emits triples, subject, relation, object, or it stops. 2 details matter. Every entity also gets an edge back to the document it came from, so provenance is structural rather than bolted on. And if it returns malformed output, the episode ends with a reward of 0. Harsh, but effective. The reader is where this gets interesting, and where Module 3 is already waving at us. It is a graph foundation model, a network pre-trained on graph structure, then fine-tuned to rank which entities support a query. 2 things to be precise about. SAGE trains its own reader. It is not the GFM-RAG model you will meet next module, which appears here only as a baseline. And the paper never tells us how many parameters it has. What is the reward exactly? 3 signals. Recall and precision ask whether the graph is a good index. Did retrieval find the right documents? Deducible asks something stricter. Given only what was retrieved, can a judge actually derive the answer? Index quality and carrier quality are not the same thing. And there's a penalty for repetition, because a writer optimizing for recall would otherwise write the same triple 40 times and call it thorough. The loop runs in 2 phases, and they alternate. Phase 1, freeze the reader and train the writer by reinforcement learning, using the frozen reader's retrieval results as the reward signal. Phase 2, take the improved writer, rebuild the graphs, and retrain the reader on those. Then repeat. Both halves get trained, just never at the same time. The paper reports up to 2 rounds, and it is the second round that produces its headline result. So what did 2 rounds of that buy? On multi-hop question answering, the best average rank in the table, and hold on to the word average because it does not win most individual cells. 0 shot on natural questions, document recall at 2 of 82.5, and retrieval latency around 0.03 of a second, the fastest system in its comparison. Then there is the second line on the board, which is a great deal less flattering. On long mem eval, the benchmark we leaned on in Part E, Sage scores 34.3 overall. The leading system scores 76.9. That is not a rounding error. That is a different postcode. And the authors say so themselves, then name the reason. The gap is in memory updating and high coverage extraction, which is Part D's lesson, arriving by a different road. Finding facts is the easy half. Retiring the ones that stopped being true is the hard half. MOS is the Memory Orchestrated Semantic System from Université Laval in Quebec, posted to arXiv in July 2026. Its one idea sits right in the subtitle, auditable by construction. Not auditable because somebody added logging afterwards, auditable because the architecture makes an unauditable answer impossible to produce. One housekeeping note, there is a second, unrelated paper on arXiv also called MOS. The one we want is 2607.04391. The paper opens with 3 commitments, and they are worth stealing verbatim. The database is the map. The documents are the territory. The index never replaces the sources. The query is sovereign. You keep the query, so you keep the ability to re-ask it. And audit everything, hide nothing. Notice what those rule out. If the explanation of an answer bottoms out in a vector space, the third principle is already broken. Architecturally, there are exactly 2 pieces. The orchestrator holds all the active code, a REST API, an MCP endpoint, connectors to whichever model you happen to be using, a component called the query profiler, and the SQL retrieval layer. The memory structure is the relational database itself, plus the conventions that organize it. That is the whole system. Graphs are stored as relation tables and traversed with recursive SQL. There is no graph engine at all. Here is the part I find genuinely lovely. MOS does not import an ontology. Its 569 concepts are induced from the corpus itself, a small hand-seeded core, a large automatically extracted layer, and a set of named entities. And the authors tried the alternatives, then wrote down that they failed. Word to Vec, then fast text, weaker. Library of Congress subject headings, fast, Roget-style thesauri, abandoned. The vocabulary that fits your corpus grew inside it. A query moves through 4 stages. 1, the agent analyzes intent. Is this temporal, thematic, affective, personal, documentary? 2, it sends a weighted profile to the query profiler, which compiles that profile into SQL. 3, execution. The SQL runs, and no language model participates in this step at all. 4, the agent inspects the results and either reformulates, capped at 15 tries, or answers, citing what it found. Intelligence at the edges, a database in the middle. Now, let us be as careful as the authors are, because this is exactly where a slide could quietly lie. Determinism here is a property of execution, not of the whole pipeline. Formulating the query is still an agent. Ask twice, and you may well get 2 different SQL statements. What you do get is that each of them, against the same database state, returns the same rows every time, inspectable line by line. The paper's own words, it must not be overread. And now the sentence that makes MOS unlike everything else in this module. Quote, MOS has not yet been evaluated on a benchmark corpus. It has been lived in. What exists instead is 13 months of continuous production since May 2025. 44 million tokens, 110,000 segments, 163,000 cataloged files, 569 concepts, 11 metadata graphs holding roughly 5 million typed relations. So what does that buy you as evidence? Durability, mostly. The system survived 4 infrastructure generations, 3 model vendors, 2 clouds, a laptop, and a server, and the memory outlived every component around it. That is a genuine architectural claim. What it is not is a comparison. The authors are explicit. No controlled comparisons against MEM0, against ZEP, against Locomo-style benchmarks. So MOS never appears on a leaderboard in this course. It is not eligible. Which brings us to the honest center of this whole module. Line up what these 8 systems actually report. ZEP, long mem eval. MEM0 and AMEM, Locomo. G-memory, ALF world, measured against no memory at all. memgraph rag, hotpot QA. Atom, one COVID news corpus. Sage, average rank on multi-hop QA. And MOS, nothing comparative at all. Not one pair of those shares a task, a metric, and a protocol. There is no leaderboard because nobody built the same track. It is tempting to read that as a failure of the field, and partly it is. But it is also information. Apply Module 1's 4-point evidence audit, and the pattern that falls out is not that some systems are better. It is that they answer different questions. So your job is not to pick a winner. It is to work out which question is yours. So, 4 axes. The first is the one Part D spent an entire video on. When a new fact contradicts an old one, what happens to the old row? Graffiti closes the interval and keeps it. Base MEM0 deletes it. And MEM0's own graph variant marks it invalid instead, explicitly so that temporal reasoning still works. Same product, 2 policies. If a regulator will ever ask what you believed in March, this axis has already written your shortlist. Second axis, how does a fact actually get found? There is a genuine spectrum here. Pure cosine similarity over stored sentences at one end, hybrid next, embeddings plus keyword search plus graph traversal, which is what Graffiti does. Then a trained neural retriever, which is what Sage uses, and which is Module 3's entire subject. And at the far end, deterministic sequel, which is MOS. This axis mostly decides how surprising your failures will be at 3 in the morning. Third axis, and it is the one nobody puts in the README. Is there a forgetting policy at all? For AMEM and G-memory, the honest answer is no. The store simply grows for as long as you run it. MEM0 has an explicit delete. A bitemporal store technically never forgets. It closes intervals and keeps the corpse, which is wonderful for audit and terrible for your disk bill. Somebody has to own that decision, ideally before procurement does. Fourth axis, the one this whole video has been circling. Can you reconstruct what the system believed last quarter? Part C gave us the mechanism, the as-of query, pin both clocks and read. MOS gives us the architectural version. Retrieval is explicit SQL, re-executable at will, and the ontology is a table rather than a latent space. The test is beautifully simple. Ask, why did the agent say that? If the answer ends in geometry, you cannot audit it. Put together, the 4 axes are a short interview you conduct with your own product. Will facts in your domain ever stop being true? Will anyone ask a question about the past? Does the store have a ceiling? And will somebody eventually demand an explanation you have to defend? Answer those 4 honestly, and the shortlist writes itself. And more usefully, most of the systems in this module remove themselves from consideration without any argument at all. Here is what all of that looks like as an actual system. Ingest raw episodes and keep them unaltered. Extract facts into a bitemporal edge store where every write passes through a contradiction check. Keep a provenance link from every fact back down to the episode that produced it. Serve reads through a query layer that takes both clocks as parameters. And log every retrieval in a form you can rerun. Nothing there is exotic. That is rather the point. And now, the discipline. When do you not need any of this? If your corpus is append only, if facts are never retracted, and if nobody will ever ask what was true in March, then a plain knowledge graph is cheaper, simpler, and faster, and the second clock is pure overhead you will maintain forever. 2 clocks earn their keep when facts supersede, when information arrives late, and when somebody expects an audit. Otherwise, do not pay for them. Let's close the arc. Part A. Static memory breaks, and it breaks confidently. Part B. 2 clocks, when it was true and when you found out. Part C. Intervals and the as-of query. Part D. Contradiction closes a fact. It does not delete it. Part E. Graffiti and ZEP, the reference implementation. Part F. 5 more systems solving 4 different problems. And today, 2 built for trust and 4 axes to choose with. Which leaves assumption 3. Look back across both courses at every retriever we have used. Personalized PageRank, Leiden, Steiner trees, best first search. Every one of them is computed. Closed form, no parameters, nothing learned. Sage's reader was the first crack in that, and it was deliberately a teaser. Module 3 takes it apart properly. GNN RAG and GFM RAG, message passing over a document graph, and retrievers that are trained. See you there.
If you like this video, please subscribe and share. Thank you.